the local protection fails to operate. The remote backup will then operate to open this breaker and so clear all of this line, as well as the bus and other outgoing feeders. When remote backup relays operate, they will generally isolate a larger area from the system and so cause a loss of power supply to more customers. The backup relays must be correctly coordinated so that they allow primary protective schemes to operate first. Only in the case of failure of the primary protection would the backup relays need to operate. We'll be looking at all of this in great detail as we proceed through this program. Remember, at this point, we're looking only at the basic philosophies behind protective schemes. At this point, let's take a break, and then we'll come back and look at some simple protection schemes. For now, please switch off the tape and review this material in your workbook. As we all know, there are many different types of relays used in protective schemes. However, most relays follow the same logic pattern. That is, input, measurement, determination, and output. The input will represent current or voltage or frequency or perhaps other values which exist in the protected circuit at any instant in time. The relay measures these values and then determines if the circuit operating conditions are within normal parameters. Under normal operating conditions, output is zero. That is, a set of open or closed contacts at rest. However, with an intolerable fault level, then the relay output will impose an operating signal on a control circuit, usually in terms of DC volts. This tripping signal is then fed to one or more circuit breakers to cause them to open so as to isolate the faulty circuit. What is the purpose of the circuit breaker? Well, obviously, the relay itself is a small, low-voltage control device, whereas the circuit breaker is an integral part of the high-voltage, high-current power system. In fact, for the protective relay to have any impact at all on the power system, it must be coupled to a switching device. The exception to this is where relays are used to give alarm only. But for action, it must command a switching operation. Conversely, the circuit breaker would have little value other than as a manual switch if it were not coupled to protective relays. The circuit breaker is specifically designed to interrupt fault current, which may be 10 times or more than normal full load current. It achieves this by breaking the current flow in a specially designed interrupter. As the contacts open inside the interrupter, an arc is drawn. It is essential that this arc be extinguished immediately and the contacts thoroughly insulated from each other, so as to prevent a restrike, which could result in considerable damage to the breaker. Various methods are used to quench the arc inside the interrupter, depending upon the size and voltage of the breaker. The quenching medium may be oil, as in the case of this 132 kV oil circuit breaker. In this type of breaker, all three phases are immersed in oil tanks, and the tanks are grounded. This is known as a dead tank breaker. We mention it here because the item does have some significance in protection, as you'll see in later tapes. Incidentally, current transformers are usually located in the bushings here. This type of breaker is usually provided with a single trip coil to operate the opening mechanism on all three phases. In rare incidences, a breaker may fail to open, perhaps due to a problem in the tripping circuit or in the mechanism itself. Indeed, as we shall see, this is one of the conditions that must be protected against. Where breaker operation is critical, an additional parallel tripping coil and circuit is often provided, fed from its own second set of relays. Another type of arc quenching is through air blast, as in this 345 kV breaker. As you can see, each phase has its own interrupter mounted on insulators. As it is insulated from ground, the tank is known as a live tank. Each of the phases is equipped with its own separate tripping coil, and they are usually, but not always, wired in series. Problems can and do occur if perhaps one phase fails to open, or conceivably all three phases open, but not at precisely the same time. This can give rise to severe transients on the system, as we shall see in later tapes. Additional redundant tripping circuits and relays are usually provided with high voltage breakers, that is 230 kilovolts and up. Yet another quenching medium is SF6, sulfur hexafluoride gas. And in lower voltage breakers, arc brake chutes are provided. Vacuum breakers use vacuum as the arc quenching medium. The subject of circuit breaker design is obviously outside the scope of this video program, but further details are provided in other programs. The important factor to remember is that the circuit breaker is capable of interrupting fault currents. There are many other switching devices, particularly in use on the distribution system, such as reclosers, sectionalizers, and oil switches. But in general, these are capable of very limited fault interruption. On the distribution system, fuses are often used in place of the relay circuit breaker combination. The fuse is not so fast or accurate as protective relays, but it does provide satisfactory economical protection for distribution transformers and feeds. Another type of protection frequently encountered at utilization voltage of, say, 480 volts is the direct acting contactor. In one common type, overcurrent causes thermal contacts to open the circuit. In another type, a built-in relay opens the contactor. However, let's return to the thrust of this program, that is, protective relaying of the power system. This circuit shows the elements of a very basic protection scheme. The inputs to the relays are provided by current and voltage. The voltage is measured by a voltage transformer connected to the bus, which may be at, say, 33 kV. The secondary side of the voltage transformer, or potential transformer as they are often called, delivers 120 volts to the relay. This voltage will, of course, rise or fall in proportion to variations in the bus voltage, so it will represent the actual bus voltage to the relay. Similarly, the line current is represented by the input to the relay from the current transformer. We shall be talking more about CTs and VTs later. This circuit breaker is located in the line, that is, the protected circuit. Let's suppose that a high magnitude fault occurs on the line at this point. The relay will detect the intolerably high current and send a tripping signal to open the circuit breaker. Let's look at this tripping circuit. A 125 volt DC system is provided for operation of the breakers. The circuit breaker closing and tripping coils are energized by 125 volt DC from the station battery, as this provides a continuous and reliable power supply. When the circuit breaker is closed, the elementary tripping circuit will look like this. These auxiliary contacts are closed,